Hello teammates, it's Mr. Nini coming to you with the solution for Friday's free response question on circuits. And let's go. We're looking at, so I gave you two circuits, two schematics for circuits. Batteries are identical, light bulbs are identical, they're in a different configuration. I'm asking for battery A, light bulb A and light bulb B, in which case are they brighter? And identified circuit 1 on the left, circuit 2 on the right. And the answer is going to be for A, it's going to be brighter in case 2. For D, it's going to be brighter in case 1. Let me take you through the why. So I adapted this from another FRQ the College Board done, just to dissuade anybody from cutting and pasting. And like you saw in my note, it got all ganked up. There's a mechanism to write your own problems on AP Classroom, but you can really only write multiple choice. So that's why I'm going to send them like I did the one this morning. And I think that'll work for this. And again, it's not a lack of trust. It's just, I understand it's very tempting. You've been raised to just kind of produce stuff, but I want you to do the thinking. It's good. Key points. And this is, I asked for a paragraph length response, and that's what I'll look for on your document. Is the key points, 5 points on this part. There's a direct link between brightness and power, and you can get it power like this. Now if you're asked this question in the exam, I would say this. I would take them through. Recall that you're going to be able to run on your equation sheet before the exam this year, so I'm going to give you some recommended equations to add. I think these derivations are right up there. For this one, it's easier to work power equals current squared times resistance. Our resistors, our light bulbs are all the same. Otherwise, we got to figure out the voltage drop is, and that makes it much more sporting. So in circuit 2, there's less overall resistance, and oops, I'm pointing up here and you can't see. Because you've got 3 branches, less overall resistance. By the conservation of charge, all of your currents got to flow through A. Because you've got less overall resistance, you're going to have greater current through A. And I would defend that. College Board has got onto the claim evidence reasoning, especially in physics. They like that. Give the people what they want. They like to see claim evidence reasoning. So D is a little harder to reason through, but I think you can get there. D is going to have more current. And here's the logic. And in a problem like this, they're not, right? If they want you to quantitatively answer this in terms of the value of I, they'll tell you something like using the variables given, using I, V, R in known physics principles, express the current in, they're going to give you that. This is more a paragraph like the response, not a semi-qualitative reasoning one. I hope that makes sense. So if they ask you for the current through A in identified variables, you got to give them something else. This one, we're allowed to kind of walk around that, and I hope that makes sense. The principle is, even though the current's going to be a little a little smaller here, D is still going to get 2/3 of the current. Where even though it's going to be a little greater here, D's only get 1/3 of the current, and that's what they're looking for you to reason. So again, paragraph length response, a different kind of answer. If they'd ask us for the current in variables, it'd be a much different problem. It's good. I'll post the key on as well. That's what I got to there. right? They're looking for a simple relationship. Do you understand? So again, when you're answering questions, ask. They're not going to say we are looking at conservation of charge and junction rule. But you're going to see this. You're going to say, there's a junction. There's a junction. That's exactly what they're getting at. They're seeing, do you understand charge is conserved in the application of the junction rule? Hot dog? Hot dog. Let's go. A little internal resistance of a battery. I think this is fair game. So you're given a value this time. The first part of the problem, you didn't have a value. You're given a value. You're told two resistors are both 10 ohms, and you measure a voltage drop across resistor 1 of 5 volts. So what that lets you do, that lets you measure the current. Because this is a series circuit, and the current through each component has got to be the same, even through the battery, right? So you've got the conservation of charge. Current doesn't stop to pick up again. It flows right through the battery. Let's call this current 1, just for fun. We didn't have to do that. So we want to get the current. We know the voltage drop is 5 volts. We're going to rearrange Ohm's law. 5 volts equals current times resistance. We're going to solve for current, 0.5 amps. I skipped a step. I would start with Ohm's law. Go to the equation on your equation sheet, start there, and walk the dog. This one you're asked to calculate. Generally, when you're told calculate, you're going to get a number. You can get away with writing this if you're told to calculate. I would link it together with words, right, like I did here. So 0.5 amps, because R2 is also 10 ohms, current must be the same. So that was a point, that was a point. Now let's get to our battery, the resistance of our battery. That's where we're asked for internal resistance. The battery, when we measure the terminal voltage, we get 12 volts. If we've got a drop of 5 volts and a drop of 5 volts, 12 volts minus 5, 5 and 5 is 10. 12 volts minus 10 gives us 2 volts. Resistance of the battery must be, we're going to rearrange Ohm's law. Resistance of the battery is 2 volts over 0.5 amps. Gives you 4 ohms. That's 1 point. Right? Because your current's going to be the same even through a battery. That's something worth remembering. Some people think somehow the current ends there and picks up again there, runs right through your battery. Let's go. Part 3. Part 3. We did a warm-up like this. It's very similar. When you're confronted with this, something like this, sometimes it helps maybe to redraw the circuit. So I did it the hard way, and then I answered it the easy way. I'd recommend you do the easy way. A couple things. Code words. When I put something in brackets like this is kind of a hot tip from me to you. Code words when dealing with capacitors. Time 0 or initial time, immediately after the switch is closed. Your circuit is just established. The capacitor just acts like a ideal wire. No resistance, right? I'm just going to leave it there. There's actually a little bit of resistance. No resistance. At our level, first year of physics, no resistance in the capacitor. And then your second code word is a long time after. A long time after. That means your capacitor is fully charged. Those going into physics, engineering, you're going to deal with time constants for your capacitors. It's not going to be quite this simple, but this is a good place to start. Just letting you know that's coming. So the switch is closed. Your current is changing V over R. V doesn't change. Your R, you can solve. So 1 over R gives you R. And so your current is V over R, easy money. Second, long time after, your capacitor acts like an open switch. It's fully charged. No current through there. all your current now is going to flow through there. You're going to get the same resistance. Now this breaks down. This breaks down, which is why I think the second part is the way to go. This breaks down. It's not... It works. I'm sorry. It works for this as it's written. I think a better way to approach this is looking at the parallel nature of this circuit, because your voltage, recall your voltage is going to be the same down both pathways. If this is cut, so we're looking at the each resistor, sorry. Through each resistor. This one will get 0. This one will get the same as it did before, right? Because this voltage will be the same, voltage will be the same, resistance is the same, resistance is the same, currents can be the same, currents can be the same. When this is closed, same voltage runs through. Current is voltage over R. You're going to get the exact same current. So we did a warm-up just like this. So we can draw it like this. Right, so your voltage is going to be the same down both branches. So if you had something like this, you cut off a branch, voltage over R is going to be the exact same thing. You're going to get the same current. I hope that's good, teammates. Send me a note if it's not. Have you a great day.